Good morning. Good morning. So I hope everybody's doing well. Happy Wednesday. Um, so let's see. We have about half the group. Let's wait a couple minutes before we jump into physics. But there were a couple administrative issues that I wanted to talk to you guys about. One is everybody got the email yesterday, or we got the email during lab about moving to pass fail. So I'm sort of conflicted about this. I don't know if it's the best choice, but uh, I think it's good in that if a student, if it's really the online transition is causing you lots of problems, it gives you a little more flexibility. So I think that's good. Um, I don't like it in that it's giving you less information about how you're doing, right? So what I'm going to do is I'm going to continue to do grades in Blackboard. You'll be able to see your progress, see how you're doing in there, and you can assess, how you're doing based on the percentage, the number value, and you can look up, in our grading scale, in the MSOE grading scale, what that would normally correspond to, and you can look up, what that would mean in terms of pass/fail. But I think that's kind of the fairest way to go about it. So if they want to, if as an institution administratively we're going to reclassify our grades in terms of, pass, low pass or fail or whatever, they can do that to give you flexibility. But you can also see your progress and see if you're if you would be doing A level work or B level work or whatever. So I think that's um, thinking about it, that's what I'm deciding to do, and I think that's the best kind of both worlds. Um, does anybody? But I wanted us to have a chance to talk about that. Does anybody have any questions or concerns about that issue? Maybe jump on the chat. Let us. I wanted to take a few minutes so that we would have a chance to discuss this. Thoughts, concerns? Homework. So this week's homework, I extended it by a day. So we'll have another day to talk about solving problems, which is what we're going to be doing today and tomorrow. So the homework won't be due until tomorrow night. Yeah. I think that's only fair considering we're kind of in the middle of talking about how to solve problems. Other questions? Oh, so what was the opinion on pass fail? I just sort of have mixed feelings about it. I think it's good in that it gives you more flexibility. It's not so good in that it doesn't give you as fine grain information about how you're doing in the course. Um, and I'm worried, that it will impact our motivation to work online. So that's my opinion. And basically, I'm going to continue to do things as I would have done. You can track your grades in Blackboard and see how you're doing. Um, and then, it will really only matter at the end of the quarter. So, but yeah, other thoughts, questions, concerns about that? I just wanted us to have a chance to discuss it. Hello. For lab, how many graphs do you need to submit? Well, that's an interesting question. And, it kind of depends on what you're doing. If we're talking about the lab this week, you might be able to show everything you want to show with a single figure. Or you might be able to make figures with more than one trace, more than one set of information. So you could have a figure that contains a lot of information. It's kind of up to your discretion. I will give you some feedback and we can go from there. Yeah. No, I think the pass-fail idea, it definitely has some positives. It gives you some flexibility, and I can see the rationale for it. Suppose you're, if you have a crappy internet connection, it's not really fair for you to be punished if that would, that could impact your course or your ability to do well in the course. Yeah, no, that's a good point too. So um, we've been talking internally a little bit about in other courses, I mean, they might not have resources for online, and in that situation, it really wouldn't be fair. I think we're doing reasonably well of you having, access to resources and tools to do well. Um, but yeah, no, that's a good point as well. For some other courses, it's just really maybe necessary to go to pass fail because they're not well positioned to do things online. Yeah, no, that's kind of the counter argument. I don't like it for that same reason, in that I am worried that it will impact our, collective motivation. That's why I will continue to post your grades. You will have a numerical grade the entire quarter, and then at the end of the quarter, that'll be turned into a pass fail, low pass, and no pass or whatever. Um, I guess I'm not really sure, to be entirely honest. I don't know. Low pass to me seems kind of like a weird concept. Um, but I mean, hopefully that provides some motivation for us to, want to do well. I'll put it to you this way. I mean, at the end of the quarter, you'll still be able to say, "Oh, I would have gotten an A, or I would have gotten a B, or whatever." And for courses like physics, that's not a small feat. I mean, it can be, if you're new to this material and applying your calc tools to this kind of stuff, it can be a lot of work. So I would like you to be able to be rewarded in that way. But I understand that, you know, uh, this is sort of a kind of a necessary thing with this online situation. So, other questions or concerns about that? Let's see. Yeah, sort of. Graduate school is kind of different. Classes are less of an issue in graduate school. Ah, yeah. So assessments. The other issue that I wanted to mention is assessments. We have to figure out a way to do quizzes and tests online. So, or we're going to try a practice version of that today. So, uh, everybody's working on their homework anyway. There will be basically a small quiz that will appear in the homework system later today. It won't be for credit. It's just for us to see if it works, for us to collectively kind of debug the system. I don't want you to walk in, to encounter your first like assessment with this system and it not work well. There be technical issues. So I'll post that later today, like a problem basically in the homework system. The way that that's going to work. Here, let me put a couple notes on the whiteboard. The way that that's going to work is it will be timed. So yeah, these administrative issues. So you can still see your numerical grades in Blackboard. None of that is going to change. All that's going to matter is this will, be an issue at the um, end of the quarter. And then assessments online. So we're going to just test it today. Um, so look forward to a short quiz in the homework system. It's going to be not for credit. And it's just to give us an opportunity to debug the system and work out the kinks before it's on something where you would actually be graded. And this will be timed. So the main issue is, online, it's just not like we were in class, right? Let's see, is partial credit possible? Are you talking about homework questions, or what do you mean by partial credit? Oh, yeah. So that's one of the disadvantages with this quiz, and that's one of the things we'll talk about, or kind of see how this goes, is I don't think there's partial credit available. It depends on the question. So it may be that there's a question that has multiple parts, in which case you can get part of the credit for the entire question. But that's one of the main flaws with this. So we're going to see how it works and then talk about it and go from there. But the main thing is it'll be timed, so you're not going to have an infinite amount of time to work on it. You'll have like 15 minutes or something. Um, and then that's fair in that everybody has the same amount of time. And then, of course, you have your online textbook. You have all these resources at your fingertips. But I want this to be a quiz of physics, right? So the timing is supposed to be a test of our ability to do problem solving in a limited amount of time. It's not supposed to be a test of our ability to Google things, but it's really on you guys to make that happen, right? I can't, I can't know. So I hope that you approach it as an honest assessment of your problem solving, physics problem solving, and not, try and game the system. Um, let's see. And, we'll do a quiz, an actual quiz after this test, probably in the next few days, or maybe over the weekend or something, depending on how this goes and stuff and what we learn from it. But that'll only be over, chapters 2 and 3. So yeah, the short sort of test quiz. This is it's not for credit. It's just to work out the kinks. Will be later today. So, but it's only going to take, it'll only take you like 15 minutes. So just to debug the system. Other questions about that? So like I said, we'll test it, make sure we understand how the system works. I just don't want you to be quizzed with this unfamiliar system, be graded, and maybe there's some technical flaws with it or something. We'll try and get those ironed out first. Okay. Let's. It will be in the homework system. Yeah, so it's time, so it'll expire. Yep, exactly. So you have to get it done by a certain time. Okay. So if there aren't any more issues, I just wanted us to take a second and talk about these administrative issues. Let's move on and talk about actual physics now. So we've been working with Newton's laws. This is chapter 4 in our textbook. And we looked at some simple problems thus far. We've looked at situations like finding acceleration of an object with an applied force. We've looked at the normal force. We've looked at basically a few different example problems. We've looked at decomposing a force vector into components in x and y. And What we want to do now is look at some more complicated problems. So, and this will be directly applicable to your homework. So let me Is it back? Is it back? Did it drop? Are we good? Shoot, I do not know. That's a new one. I hadn't had it drop. It dropped on my end. Sorry, guys. Let's see. So are you able to see? Yeah, we have the whiteboard. Okay. Well, hopefully we don't, we're not plagued by that issue. That's obnoxious. We want to look at some more complicated problems. The scenario that I wanted us to look at was basically if we have two objects in contact with each other. It's not a very good job of being in contact. And we're going to apply a force. And basically, we want to understand and work out what the contact force is going to be in between these objects. But this gives us an opportunity to talk about some of the ways of setting up more complicated problems, because now we have two objects instead of one. So the first thing that we would do is let's put in all of our forces. So maybe we'll draw those in a different color for the time being. So like we've been doing before, let's break this up into free body diagram. Let me abbreviate that by FBD. How about? Save a little room. So what forces do we have? On mass 1, we're going to have the applied force. We're going to have the force of gravity that's pointing down. We're going to have the normal force that's pointing up. And we're also going to have, on this one, the force of 2 on this block. Okay. And then if we look at M2, it's very similar. We're going to have M2G. We're going to also have, the force, the normal force for this one. Now, we're going to have an equal and opposite force on this one, F1 on 2, I'll call it. And those are the forces that we have applied to the second block. Okay, so this is a simpler version of a problem that's in the homework that's more complicated. You have more objects. So we've annotated our picture. We have all the forces in there. So the next thing that we want to do is apply our Newton's laws. So in this situation, first, let's look at the whole system. We know that if these are running into each other, you push on the one, it's pushing on the other one, it's going to accelerate the whole system. So in other words, if we sum the forces in the x direction for this, all that there is, we're not going to be dealing with the internal forces, the contact forces. On the total system, we just have F. We know from Newton's second law that's going to equal ma. Well, m in this situation is the sum of the two masses. Okay. And then the forces in y, there's nothing happening in y because the objects are just sitting on the surface. Okay, so we're just looking at the sum of the forces in the x direction. Now, let's look at M1. So for M1, we sum the forces in the x direction. What do we have? Well, we have F. We also have this force 2 on 1. So we can tell from our picture that this is going to be negative. I'm just going to write it in as if we do not know anything about it, except we know that it's in the x direction. And why I'm doing that is because that will help us keep straight our signs. So something that can be confusing about this is, well, is the sign of this negative, or did we already put this in, etc.? So what I'm going to do is I'm going to leave it general for now. And then according to Newton's second law, this will equal the mass of 1 times its acceleration. Okay. Okay. So, and then let's also look at M2. Oh man, my sigmas. If we look at M2, whoa. The sum of the forces in the x direction, what do we have? We have just F1 on 2. And in this situation, well, for this part, that will mean that this is equal to M2 times the acceleration. Okay. So the other thing that I want to note in this is that we explicitly know that F2 on 1 is negative F1 on 2. Okay? And this is a statement of, Newton's third law. Okay, or a realization that comes from that. Either they're equal and opposite, equal in magnitude, but opposite in direction. Okay. So we can ask some questions now. We want to know, what's the acceleration of the system going to be? Let me see. Let me write it over here. How about? So we can keep it on the same page. So what's the acceleration? Well, if we look at, let me label these. How about 1, 2, 3. If we look at our first expression, we can just solve that directly for AX. All we have to do is divide by the mass. So if we do that, we get F. The acceleration is F over M1 plus M2. Now, if we've set this up correctly, that should be the same as if we combine equations 2 and 3. So how do we do that? Well, we can substitute it in. So let's see here. Notice if I substitute in what we know here, and then I put what that is, if I subtract this term over, divide, we get the same thing. So this would be F and we find the same thing. And we should, because this should be all consistent. Okay. So this is just an example of how being more methodical about it or helps us keep track of the signs. And this is looking at this in two different ways, we get the same thing. So that gives us confidence that this is right. Granted, this is a really simple example. But the other thing that we would be interested in is, well, what is this contact force? What is F2 on 1 or F1 on 2? So let me write that below here. Okay. So what we can do for this is we can substitute in directly. Let's look at, if we look at 3, we have from there that F1 on 2 is m2 times the acceleration. We know the acceleration now. We can put that in there. We find that it's m2 f Okay. So we now have an expression for F1 on 2. Now, we should be able to get the same thing if we look at our other expression. It should all be consistent. So let's try that. If instead we look at 2, okay, what's our starting point? We have F plus F2 on 1 equals M1A. Okay. Let's put in our acceleration again. And we'll subtract over the F. So F2 on 1 is going to be M1A. Oops, let me substitute in what that is. M1 times F over M1 plus M2 minus F. Now, we can put these on a common denominator, right? If we were to multiply this by M1 plus M2 over M1 plus M2. Okay. So if we do that, what do we get? We get M1F minus F M1 minus F M2 all over M1 plus M2. Notice this M1F and this are going to cancel. And so we're left with F2 on 1 equaling negative F M2 over M1 plus M2. Okay, so notice this is exactly the same thing within a sign as to what we got up here. And so we have shown that those two forces are equal in magnitude but opposite in direction. And this shows us that our math is consistent. So this is just an example of two masses in contact. You can imagine, so this is directly applicable to one of the homework problems, but you can imagine this is also applicable to the situation where you have, instead of objects in contact, what if you had objects that were connected? Actually, let me draw this a little bit bigger. Suppose you had objects that were connected by like a cord or a rope or something, and you could pull on one. What would happen? There would be a tension directed to the right, and then there would be an equal but opposite tension directed, and oftentimes we write this as Ft or tension. There would be another tension that's going the other direction that would be equal in size but opposite in magnitude, or sorry, equal in size or magnitude but opposite in direction. And this is sort of the simplest example because it's just one dimension, just resting. But you can imagine solving the same kind of problem. You could find the tension in the cord. You could look at the total system and then find the tension in the cord. So it's sort of the same math. And this will be applicable to things that we talk about later when we're working with situations where there's a cord like over a pulley or something like that. But it gets at this issue of why this tension force is in the opposite direction, but it's the same size. Okay. So are there any questions about this this setup, this kind of simple problem? Let's take a beat and just see if anybody has any questions. You can put in the chat. Is everybody good? How about put a thumbs up in there if everybody's on the same page. Maybe I'm beating this to death. Let's see. Oh no, thumbs down. Conceptually, is F2 on 1 M2 resisting the push from M1? Yeah, you can think about it that way, sure. You can think of that as like there's additional mass there. It requires that those forces be in balance for those objects to not be accelerating relative to each other. But that additional mass would be resisting the acceleration because we know from Newton's second law that the acceleration is inversely proportional to the mass. Okay. So we're doing okay, more or less? Okay. Okay, cool. Yeah, there is a problem just like this that is in the homework that has a lot of steps. So you can it'll guide you along breaking it out. It'll also have you calculate some numbers. So another way to think about this, actually, it occurs to me is, if this were not to be the case, if these forces were not equal in size, what that would mean is that they wouldn't be balanced, and you would have one object accelerating relative to the other, which wouldn't make sense. So, okay, so let's look at another situation. Okay, so this is a very important system that if you were in lab this week, we already talked about it. So this will be a little bit of sort of ground that we've already been over. But this will be relevant for the homework as well. And that is the situation of the inclined plane. Okay, so, or really it's a block on an inclined plane. I can tell you that this is a problem that consistently, for some fraction of students, causes confusion. So I really want to spend a little bit of time looking at this. And then if we already talked about this in lab, sorry, this will be a little bit of review, but it's really a system that you want to own and be able to derive. So the question that we want to look at with this is you have some wedge. It's got an angle theta. We have our block. The block has some mass. Now, in lab, we talked about the situation where there's friction. We're not going to have friction for the time being. But what we want to understand is, how does this thing accelerate? And, what is the normal force? Okay. So how do we approach this? Well, let's draw in our forces. We're going to have the force of gravity pointing down, as always. Now, what we're going to do is we're going to employ a problem-solving trick where we're going to rotate the coordinate system so that it is along the axis of the wedge. And the reason that we're doing this is because if you were to instead keep the coordinate system like this, notice as the block slides down, it's accelerating in both the x and y direction at the same time. So it's a lot more complicated problem to solve. So instead, we tilt the coordinate system. Now it accelerates along our x-axis, but it's constrained on the wedge. It can't accelerate in the y direction. So it takes this two-dimensional situation and makes it one-dimensional. This simplifies the situation, but it adds a complication in that we need to now decompose our force into the force of gravity into components that are perpendicular, i.e. in the y direction, and along the wedge. So if we do that, one of the ways you can think about this is imagine folding the wedge flat, right? Like if you fold this thing flatter, theta is going to shrink. The block would come down as well, and this angle here would also shrink. That's because that's also theta. Okay. So we need to identify the components. This one, you can see this is opposite to theta. This would be mg sine theta. This one over here, it's adjacent to theta as we have it in here. This would be mg cosine theta. Okay. So we have identified force of gravity down, the component that's along the x-axis that we have, and the component that's perpendicular. The other thing that we need to put in is our normal force. So the normal force, our perpendicular to the surface force, will be like that, and it will be opposite to the mg cosine theta piece. Okay, so to our questions, how does this accelerate? Well, we can do like we've been doing in the past. Let's sum the forces in x and y. If we look at the sum of the forces in x, the only component that we have for this frictionless case is mg sine theta. That's going to be equal to the mass times the acceleration, according to Newton's second law. Notice that m appears on both sides. So the acceleration is g sine theta. What about the normal force? Well, if we look at the sum of the forces in y, what do we have? We have F normal, we have minus mg cosine theta. That's going to equal, in this case, ay is 0. It's not jumping off the surface of the wedge. So the acceleration in the y direction is 0. And so if we then solve this for the normal force, we can see that it's mg cosine theta. Now, this will be relevant to friction, which we talk about in the next chapter, and which we'll talk about in lab, which we're talking about in lab this week. So, a couple things I would mention, or one thing that I want to emphasize is, this is such a fundamental system. I think you should be able to basically start with a blank piece of paper and come up with this acceleration and what the normal force are. Let's see, because questions. So yeah, this is theta always the value for the component decomposition. So why part of why I'm really emphasizing this problem is because I've noticed this is consistently confusing because we're accustomed to seeing theta and x and thinking, okay, cosine theta, that gives you x, right? Not in this situation. So we have to be careful, okay? So I would say, be able to derive on your own. And, really the sooner that you kind of have this problem totally under the belt, the easier it'll help you with doing other stuff that's more complicated. Another thing that you can do is, to help us keep straight, is look at the limiting cases. So, and what I mean by that is, look at what happens when theta goes to 0 or theta goes to 90 degrees. So in this case, if what's going to happen as theta goes to 0? What's going to happen to the acceleration? Yeah, there won't be any acceleration if theta goes to 0, because the acceleration depends on sine theta. As theta goes to 0, sine theta goes to 0, and that's what you expect. I mean, that would be the situation where the thing is resting. Now, sort of the opposite extreme is what happens when theta goes to 90 degrees. In that situation, sine theta goes to 1. So the acceleration goes to g. And that would be the situation where now it's totally, it's vertical. And it would just fall and be in free fall. And you can apply the same logic to the normal force. So the normal force, normal force for theta equals 0. What happens to it? It becomes mg. And that makes sense. You recover just the weight. And likewise, the normal force for theta equals 90 degrees goes to 0. And that makes sense because look at this situation. If it's falling, there's no normal force. Okay. So my apologies to those of us who we talked about this yesterday, but this is such a fundamental problem that I think it's good for you to see it a time or two. We'll talk, we can review this again in lab for those who have lab on Friday. Are there any questions about this system. Okay, so what I want to do is give you some an example problem to look at with this. That has some actual numbers, so this will be a little more similar to homework. Okay, so let's see. We have a block shown in this this figure. It has some mass and lies on a smooth, frictionless plane tilted at an angle of theta equals 22 degrees. We want to determine the acceleration of the block, and we're given that if the block starts from rest 12 meters up the plane, what will be the block's speed when it reaches the bottom of the plane? So let's see. We're given basically that this is 12. Okay. So, well, let's do the whole thing here. We'll do our free body diagram. We have mg pointing down. Notice they have helpfully given us a coordinate system that's aligned along the wedge. mg is pointing down, mg sine theta along the ramp, mg cosine theta perpendicular to it, the normal force perpendicular to the ramp in the other direction. We sum the forces in our x direction. We have mg sine theta equals the mass times the acceleration. Notice the mass will cancel. Solve for the acceleration. So I know I showed you how to do this already, but I think it's good to just emphasize, to reinforce. We have our expression for acceleration is g sine theta. So kind of interesting, right? It does not depend on the mass, the acceleration. You could change the mass, it'll accelerate at the same rate. If we plug in g, 9.8, and our sine, 22 degrees, what do we get? I have to look it up, actually. Sorry. Oh, you beat me to it. Yeah, so you would get an acceleration of 3.67 meters per second squared. Excellent. Okay. So we've just applied this ramp situation that we've been talking about to find the acceleration. Now, if the block starts from rest up this distance, we want to know what its final velocity is going to be. So this is basically part A. To find v final, so we have a distance and we have an acceleration. How can we go about that? We can use our expression for v final, that v final squared equals v initial squared plus 2 times the acceleration times the distance. We can solve this for v final. So we know it's starting from rest. So this will be 0. V final will be the square root of 2 times the acceleration times the distance, be the square root of 2 times 3.67 times 12. If we put in our numbers, we'll find that this is 9.4 meters per second. And if I'm being diligent here, we would indicate this direction as the I hat direction because it's along the X direction in our picture. Okay. Yeah, good point. Yep, I hat. Yep. Good catch. Okay, so this is sort of, the starting point with this. Let's ask a couple other questions about this. Oh, shoot. Ah. Wait a second. Why am I... Whoops. Hotkeyed something. Sorry. Technical difficulties. I can't cut and paste, basically. Sorry. Okay. Wait, why is it... Sorry. Okay. Anyway, question. So how is the angle theta the same as the given angle? I guess I don't know what that property is. I think you can see that most clearly just looking at the geometry of the system. What I would recommend, the angles change in proportion to each other. Yeah, so I mean, think of it this way. If you can draw yourself a picture to kind of visually show this. So if this is theta, imagine then drawing the case where this is very gradual. You can see that this component is going to get smaller while this one is going to get bigger. That's how I think about it, how I can associate those two angles as being the same. Okay, so let's look at these last couple things that we can ask about this question. So now we're given a slightly more complicated. We're given one additional detail that now the block has some initial velocity. So let me draw a picture again. You always want to draw a picture. So now it's going to have some initial velocity up the ramp. And we want to figure out how far up the plane is going to go. The plane it's going to go. So we can use the same math that we did before. So this is really the same problem. Let's call this part C. Now, our V final. So again, we don't have. We're not talking about time. But we have a distance. We want to know the distance. We have an initial velocity. The final velocity, what's going to happen to the final velocity once it gets up to the top? It will stop. It will come to rest. So up here somewhere, v goes to 0. at the top. And so then we can solve this for distance. If we put in our numbers, we come up with a distance of 2.8 meters. So that's the distance in x, right? So if we were being careful about this, this would be, really this is in the negative I direction in our picture. And then sort of the other part of this in terms of height. So what does that mean? Well, we have to use a little bit of trig and figure out if we have something that went up 2.8, and this is, theta equals 22 degrees. What is this? Well, we can relate the hypotenuse to the height via sine theta. So we know the height is 2.8 sine theta. And if we crunch the numbers, we find that this is about 1 meter. So this is the height. Okay. I don't want to spend too much of your time, but let's look at this this last section here. So the last part, how long does it take for it to slide up and come back down? So these questions it may look unfamiliar, but this is totally a remix of stuff that we did in Chapter 2. Basically, we're using our kinematics expressions. Now we want to know, how long does it take to go up and come back down? So it's going up and coming back down. The acceleration is no longer g, but this is the same situation as if you were to throw an object up in the air and wait for it to come back down. So one way to do this would be to say, look at our x equals x, x initial plus v naught x, v naught t rather, plus 1/2 at squared. We can realize that if we're going from one position and back to the same position, these will be 0, or they'll be the same, so they would cancel and give you 0. And so we'd have something that says now we have a factor of t that's common. So we can then solve this for, the remaining factor of t here. So we'd have negative v naught. We'd pick up a factor of 2. And divide by our acceleration. Notice the acceleration, let's see. So if we put in our numbers here, the way that we're talking about this now, technically this v naught is negative in our coordinate system. So really this would become positive. Our acceleration is positive because it's along the x-axis in the positive x direction. It's a little confusing because that's not what we're accustomed to when we think of an object throwing up and coming down. We think of g as being in the negative direction, but in this coordinate system, those things are positive. So if we put in our numbers, we get a time of 2.5 seconds. Okay, so this is just an example. It shows you applying Newton's laws and combining that with our kinematic expressions that we were working with in Chapter 2 and Chapter 3. Questions on this system. So this is an important system. Like I mentioned above, be able to come up with the block on the plane on your own. Just to re-emphasize that. Questions? Put it in the chat and we can chat for a second. Sorry we went a little bit over, but this I just wanted you to see some different examples, kind of combining with things with the block on the plane. It's such a I'm sort of emphasizing this to death, but it's just such an important system. You'll see it again when we talk about friction. Can put a couple notes down here. So questions? Good, everybody's okay? Maybe I was going a little bit too slow. So stay tuned for our practice quiz. Yeah, the homework has been, I changed it to be due tomorrow. And then, tomorrow we'll look at some more problems. We'll look at, we'll look at basically things that involve pulleys, some more complicated stuff. Other questions? Yeah, we can do office hours after this. Yep. Yep, we can look at combining pulleys and ramps. Absolutely. We'll look at that tomorrow. There's a question in your homework that's about that. That's part of why, that's a big part of why I pushed the homework due date back by a day. My observation last quarter was that students, for a chunk of students had found the ramp to be really confusing. So I wanted us to spend kind of a lot of time going through that in detail. So that's totally fine. I'd rather head off confusion than try and help people get unconfused. So let's, for those who have seen it before, I'm sorry, we're going kind of slow, but we'll look at more complicated stuff tomorrow. Other questions? So if you have lingering questions on this stuff, put it in the comments below, and I can respond to you there, or reach out to me on Teams. Otherwise, good point about office hours. We can do office hours at 12:30. I'll get a piece of toast here or something, and then we can do office hours. That's on the Go board. So I put a link actually in Teams to the Go board as well. Okay. If everybody's good, we will see you tomorrow.